Yes, good morning to one and all. This is the continuation from the last class. So, we derivated the equation of this 2 from this equation 1, right? In the last class, we derived this second equation. So, the parameters of Km and Vmax can be assessed from the plasma concentration time data collection. So, when you give the drug through IV bolus administration, which is following your nonlinear pharmacokinetics, so we can able to estimate the Michaelis-Menten constant, that is Km, and the theoretical maximum rate process, that is of Vmax. So this is of our basic Michaelis-Menten equation. From this equation we derived this log equation. So then the continuation from this slide is a semi-log plot of C versus T, that is plasma drug concentration versus time. It yields a terminal linear portion. See how the terminal linear portion. See ma'am, here this is log C and here in the x-axis you have T. T versus log C. So when you plot this graph, the curve is appearing like this. This is called the terminal linear portion of the curve with a slope of our theoretical maximum rate process by 2.303 km. So this is what the terminal linear portion of the curve with the slope. So here you will take this log C. So this is normal graph, that is Cartesian graph. So when you take semi-log graph, you will take directly the log values. Okay. So here in the written matter, see a semi-log plot of. So here you are going to use semi-log plot. So for that you can take log C values, log concentration values versus T. T is normal values, normal time values. Okay. So the slope is minus Vmax by 2.303 km. So when you back extrapolated, see how you will take the back extrapolated concentration. See ma, from which point of this log C concentration your curve is going to start. You can consider this as a initial plasma drug concentration. That's why it is a C naught. So here we are considering log values. That's why it is log C0. So when you extrapolate this curve from this curved part to the straight line that will joins your y-axis, you can consider it as back extrapolated plasma drug concentration. So which plasma drug concentration you are going to back extrapolated here? Initial plasma drug concentration. So that's why it is log C naught. Then what is this arrow mark? This is forwarded arrow mark and this is backward arrow mark. So this is C0 backward arrow mark. That is indicated you back extrapolated line of the initial plasma drug concentration. So we will get this back extrapolated plasma drug concentration from this curved part. When you back extrapolated your line, then you can get the value of log C0 back extrapolated concentration, that is C0 extrapolated symbol. Then for this analysis, so you have to analyze this slope and the C naught and the C naught back extrapolated concentration. You can utilize the equation of minus dC by dt is equals to Vmax by 2. Where we observed this equation? That is the first situation of Michaelis-Menten equation, that is Km is equal to C. So that's why I have written here like this. So for this analysis, take the equation into consideration, that is When Km is equal to C, we get the equation dC by dt is equals to Vmax by 2. So then the equation that describes the line, that is this line, this curved line, is log C is equals to log C naught minus Vmax into T by 2.303 km. From which equation you will get this equation? From this equation we get this equation. See, first everyone has to write this second equation, that is log C is equals to log C naught plus C0 minus C by 2.303 km minus Vmax into T by 2.303, not 0 here. Okay, km. So first you write this equation. From this equation 2 we will get this equation 3, that is directly we don't have this term C0 minus C. Why? Because here this C0 minus C values are normal, but here we can take the log values. So you can neglect this whole term. Then the equation will becomes log C is equals to log C0 minus of Vmax into T by 2.303 km. Is it right or not? So that equation is directly comes here. In your textbooks, directly they have written this equation without writing this equation. So you must follow the slides, what I am telling you. Then once again you write the second equation and then the third equation. Then at low concentrations, what is the low concentrations of the drug? At low concentration of the drug, the above equation 2 and 3 becomes identical. That means these two are looking like same at the low plasma drug concentration levels. So there is a need to simplify it further. Then we will get, see ma here, log of C naught by C. Here our C naught value is back extrapolated plasma drug concentration levels. Okay. So here it is log C naught. This is normal C naught value and this is back extrapolated C naught value. That is equals C0 minus C by 2.303 km. Then what happened to these parameters? These two are same. Then these two will get cancelled. So when you extract this C0 back extrapolated concentration with the initial plasma drug concentration, you can write this equation directly. C0 minus C by 2.303 km. Here we are considering this extrapolated concentration. The equations are very simple as compared with one compartment open model. Only one thing, you have to write each and every time which equation we are getting this equation. So you have to write. See here, without writing this 2 and 3, how you can able to know how you will get this equation? Likewise. So here once again you have to write it 2 and 3. Then from this 2 and 3 we will get this equation. These two are identical, so these two will get cancelled. Then we can extract this whole term. Then you will get like this. And here we are concentrating only on initial concentration and the back extrapolated concentration. So that's why the equation is like this. And then this is all about the estimation of Vmax and Km. By the three different situations, we will get three different equations. That is one part under Michaelis-Menten equation. And then you have one more alternative approach. This is also used to estimate the Vmax and Km. So whenever they will ask you to write Michaelis-Menten equation, you have to write up to this mark and including these points also. This is an alternative approach, and here also you have three different methods to estimate this Michaelis-Menten constant and the theoretical maximum. So this is what the next enzymatic kinetic classic Michaelis-Menten equation. This is used to estimate the Vmax and Km by an alternative methods. So general Michaelis-Menten equation is like this, right? Vmax into C by Km plus C. This equation, we all know about this equation. This is the general Michaelis-Menten equation. But this equation is enzymatic kinetic work. The Michaelis-Menten again derived this equation in a classic model. So for this alternative approach, you can utilize this equation as a basic equation. So what it is there? Km plus C. Instead of C, here we are writing Cm. So what do you mean by Cm? Cm is the midpoint. Cm is the midpoint of substrate concentration. M stands for midpoint. C stands for concentration. Concentration of midpoint interval of substrate. So I will tell you how you can take this midpoint. So first you should remember this equation. Minus dC by dt, Km plus C. Instead of C, here Cm is there. And Vmax into Cm. And dC by dt is the rate of reaction at various concentration levels of the drug, that is Cm. So here this alternative approaches, every method, these three methods you can utilize the midpoint concentration levels only. You cannot take directly the concentration level always. You should take the midpoint concentration levels. So then we can estimate in vitro experiments or in vivo experiments at a constant enzyme levels. So how you will take the midpoint, right? Suppose, for example, I am telling the concentration levels are 10, 20, 30 microgram per ml range. So for 10, initial concentration it will be 10. Okay. So then the next concentration is 10 plus 20 by 2. Then you will get 30 by 2. Then you will get some x value. This is the midpoint of the concentration. So you can take the midpoint of the concentration like this. For each and every concentration, you can calculate it. Okay. So this is the midpoint calculation for concentration. In some experiments, you are going to calculate same midpoint for time. So here also same thing. You can add these two subsequent concentrations, then multiply, then divided with 2. Then you will get one value, that is indicated you the midpoint of respective concentration or respective time. So this is the calculation for midpoint time or midpoint concentration. So I already told you, in the alternative methods you have three different kinds of methods. Under that I am going to discuss you about the first method. So the first method is linear Burke plot. So this is an alternative method to estimate Km and Vmax. So this is the first method. So for getting this equation 2, first you can write the equation 1. What is that equation 1? dC by dt is equals Km plus Cm divided by Vmax into Cm. First you can write this equation. Okay. So this is the classic Michaelis-Menten equation which is utilized to derive an alternative methods for estimating the Vm and Kmax. Vm and Vmax and Cm. So first method is linear Burke plot, that is the method 1. First you can write this equation. This is equation 1. From this equation you will reciprocating the equation. If you reciprocating this equation, you will get this equation. Write down this equation. 1 by dC by dt is equals Km into 1 and Vmax into Cm. Km, here you have a addition symbol, right? So Km into 1 divided by Vmax into Cm and plus 1 by Vmax. You can write it down like this. This is the reciprocating equation of this equation 1. Here, Cm is the plasma concentration at midpoint of sampling interval, and a double reciprocal plot of linear Burke plot. So you can plot the graph between 1 by dc by dt, this parameter, versus Cm. Then it will yield the straight line with the slope of Km by Vmax. So intercept is y by Vmax. This is the intercept. See, first you should write clearly the equation 2. Then you can able to find out from which points we will take into consideration to plot a graph or to graph a, okay, to plot a graph. See here, this is one parameter, 1 by dc by dt, and here we are going to stress about this Cm. This is plasma concentration at midpoint of sampling interval. Here we are stressing out only this midpoint of concentration. So you can plot the graph between 1 by dc by dt versus the Cm. Okay. So you will get y-intercept as 1 by Vmax and Km by Vmax as a slope. First you should write this equation clearly on your white paper. Then you can plot this graph. This is very easy to learn. See, the graph we should plot it here with the help of 1 by dc by dt values and 1 by Cm. Then we will get the slope of Km by Vmax. And here 1 by Vmax is there. From which graph we got this graph? From which graph? I already told you, when you take the concentration, concentration versus time here, okay, you will get graph like this. So from this point, we had some Vmax by 2 value. Okay, this is the basic graph. So that's why this axis is touching this y-axis. So here it is 1 by Vmax. So this is the y-intercept. Intercept means what? At which point the line will joins the axis. At which point the line will joins the axis. This is of your y-axis, right? So this is called the intercept. So here your y-intercept is 1 by Vmax and slope is Km by Vmax. It's a very simple graphs. So you should learn it. Okay. So this is a plot of 1 by dc by dt versus 1 by Cm for determining the Km and Vmax. Once again, I am telling you, ma, your textbook is not at all clear. Okay, I struggled a lot to draw all these things. So you have to remember like this. It is easy. And one more important thing, I already told you, you have three different methods, right? This linear Burke plot is the first method. But this method is having some disadvantages. What is the disadvantage? Here, the plot points are clustered. Only one disadvantage they mention. So, while plotting the graph, here some points are clustered. So, that's why two more scientists will describe you for determining this Km and Vmax, these two equations. More reliable points in which the points are uniformly scattered. And in case of linear Burke plot, they will be clustered. And here they are uniformly scattered. What do you mean by scattering? See, this is the axis, no? So, the points will be scattered like this. At least you can join 2 or 3 points, not all points. Then it will give you some straight line. That is what the scattering. So more reliable points in which the points are uniformly scattered. This will be explained by Hans Wolf. He is one of the scientists. That's why this plot is called Hans Wolf plot. You can multiply the equation 2 with Cm. Then you can get this equation. Then you can write it here. What do you mean by how your equation 2 will be? Just write this equation 2. This is 1 by dc by dt. So you can write it here. 1 by dc by dt is equals, you can write it here, 1 by dc by dt is equals km by Vmax into 1 by Cm plus 1 by Vmax. This is what we get under equation 2, that is linear Burke plot, right? So first you can write this equation. Then we will get this equation 3 from this equation by multiplying this equation 2 with the Cm, that is the midpoint of sampling interval. So you can write it this. So when you multiply this C with the Cm, here the Cm will comes divided by dc by dt, then Km by Vmax is as it is. You can multiply it with Cm, no? So Cm by Cm is get cancelled. Then here Cm by Vmax. How simple it is? Once you have to write the second equation. That is the concept. So we can multiply the second equation with the Cm. We will get this equation like this. So here from which points you have to take consideration to plot a graph? See, Cm divided by dc by dt. This is one parameter, and the second parameter is midpoint of concentration levels, Cm. Then it will give a straight line with 1 by Vmax as a slope. This is 1 by Vmax as a slope, and this Km by Vmax as a intercept, as the y-intercept. See, you can plot the graph between dc by dt versus Cm, 1 by dc by dt, right? Then Cm. Then you can yield 1 by Vmax as the slope and Km by Vmax as the intercept. Shall we look into it? See here. This is Cm by dc by dt. This is Cm. We will take these two parameters to plot the graph on x and y axes. See here. This is the slope we will get here. 1 by Vmax, not V. 1 by Vmax. Okay. So this is y-intercept. Y-intercept. That is Km by Vmax. So the slope is 1 by Vmax. Is it right? Here the straight line 1 by Vmax as the slope and Km by Vmax as the y-intercept. Simple thing. Only one thing, you have to write the equation, then which parts you are going to take into consideration to plot a graph. On what parameters? Here the midpoint of time interval and the rate process, and here only the midpoint of concentration intervals. So then we will get slope like this and y-intercept like this. This is what Hans-Wolf plot. And the third scientist, this is Augustinson plot. This is the third method which is directly estimated the Km and Vmax parameters. So you can write this equation directly. From which equation you get this equation? From equation 1. So first you have to write dc by dt is equals Vmax into Cm by Km plus Cm. First, everyone has to write this equation. From this one equation, one of classic Michaelis-Menten equation, we will get this fourth equation of Augustinson plot. So see here, what is the variation between these two equations? dc by dt is as it is. Vmax, you can write this Vmax like this, and then minus of dc by dt into Km by Cm. So first you can write this, then you can write this. After writing this first equation, you can write one sentence like rearrangement of the basic classic Michaelis-Menten equation. We will get this Augustinson plot equation. Just that sentence is enough. Then you can plot the graph between dc by dt versus dc by dt divided by Cm. See. Then it will give the slope of minus Km and intercept of Vmax. See, dc by dt versus dc by dt divided by Cm. then you will get the y-intercept of Vmax and the slope of minus Km. So this is the Augustinson plot of dc by dt versus dc by dt divided by Cm for determining the Km and Vmax. These plots graphs are also not clearly mentioned in your textbooks. You have to write it down as it is. So this is of different methods or alternative methods which are clearly explaining us to determine the theoretical maximum of the rate process, that is of Vmax, and the Michaelis-Menten constant, that is of the Km. Okay, these three methods are useful as an alternative methods. Okay,